Ladies and gentlemen, it is 4 o'clock on a Thursday. What does that mean? Well, these days that means it's time for Hot Technologies. Yes, indeed. My name is Eric Cavanaugh. I will be your host for what I am sure is going to be a very interesting conversation. We're going to talk about a revolution. That's right. Software tends to move in two ways, evolutionary and revolutionary. Of course, the evolutionary approach is when you have these small incremental improvements over time to a platform. But once in a while, we see these revolutionary changes. Someone's got their speakers on. Watch out for your speakers in the background, folks. Once in a while, you see these revolutionary changes. And let's face it, we are at that time right now. We are at that inflection point. It's happening today. We're going to talk all about it on Hot Technologies. So there's a slide about yours truly. You can follow me on Twitter at Eric_Cavanaugh. Of course, we also have at the Bloor Group, I believe. You can follow that. We have a lot of handles, in fact. So follow us on Twitter and follow us on LinkedIn if you would be so kind as well. So this year is hot. We're seeing a lot of very interesting stuff happening. I, of course, have been following the data warehousing field for quite some time. I used to work at the Data Warehousing Institute, which, of course, tells you that they're focused on data warehousing. And really, if you look at the history of using information as an asset to improve decision-making, well, that all boils down to analysis. You have to get a bunch of data, organize it, normalize it, start running some algorithms to understand what's happening. A lot of that boils down to segmentation, quite frankly. A lot of it boils down to predicting who is likely to buy this product or that product. It's a good practice to figure out who is going to commit fraud, for example. So a lot of the really cutting-edge stuff in analytics has been focused on fraud for years because, let's face it, it's pretty complex stuff. But you can crack the code. You can figure out what's going to happen. You can at least give yourself a lift or an added advantage, and that's all been revolving around data. Well, if you look at the last 5 years and how this whole Hadoop open source movement has really changed things.
Participant lines muted.
What you can see is that a lot of things are going on, and these are not small changes that are taking place, folks. These are very, very significant changes. And the open source movement really has fundamentally altered how we look at the entire world of enterprise software. And if you look at how some of these developments are altering the nature of what you can do in these environments, well, let's face it, it's a pretty big deal. So when I heard about Snowflake, the company that's in the Hot Technologies webcast today, I just kind of felt it initially, and upon investigation have, at least so far, certainly had my suspicions validated, which is that these folks took a very hard look at the traditional means for doing data warehousing, and they realized that if they started from scratch, they could leverage a number of the innovations that have taken place in these last few years to offer what is, quite frankly, a whole new level of capacity, of capability in the world of data warehousing. So I'm very pleased to have a couple people online today. We've got my good buddy Rick Sherman from Athena IT Solutions. He's been around for a number of years and on the front lines working with data warehousing, feeling the pain of data integration, feeling the difficulties of dealing with ETL and all the hard stuff that goes along with the engineering side of data warehousing. We have our very own Dr. Robin Bloor, Chief Analyst here at the Bloor Group. He trained as an actuary some time long ago, so he understands the mathematical side of the equations. And then we have Bob Muglia, CEO of Snowflake Computing, and he's got a long history as well, and he can talk about some of that. But this guy really understands the underpinnings of data warehousing, so we're pleased to have him on the line today to share his thoughts as well. So first of all, we're going to hear from Rick Sherman, then we'll hear from Robin Bloor, and then we'll hear from Bob. This is different from a briefing room. For those of you who check out our shows often, we kind of turn the tables here. We have the analysts go first, and they give their take on what you need if you are going to be a vendor in a particular space. And then the vendor really kind of answers to them and says, well, you know, Rick, you said this, and we have that. Robin, you said that, we have this, and here's how we pieced it all together. So we're going to learn about what Snowflake has done, and they've just launched GA, as I understand it. So this is really hot off the press. It's perfect for a hot technology. I'm getting a bit of background noise. Oh, we're going to try to watch out for that. Speakers, make sure that your computer speakers are off. And with that, I'm going to hand it over to Rick Sherman. Rick, welcome back to our show. Click anywhere on that slide and take it away.
All right, thanks, Eric. So I have the task of starting off the session by trying to give a background to where we are with traditional data warehousing, the changes, some of them revolutionary, are happening in that space, why there's a need for some more things to happen to make it easier to do, and then finally a few suggestions, and then we'll hand it off to Robin and Bob. So from a perspective of a traditional data warehouse, and I have been doing this almost for 3 decades, so for quite a while now. The traditional warehouse, we have the sort of the enterprise data warehouse built to accumulate data from numerous source systems. And then people put it into, sometimes referred to as a hub and spoke, put it into some schema set up for business intelligence, so then people can use analytics and BI to business intelligence tools to be able to analyze. The data warehouse goal is to integrate, cleanse data from various source systems. Traditionally, that's been in a relational database. And then there's been various technologies used in order to put it into things called data marts, online analytical processing cubes, et cetera. But this classic hub and spoke model has been around for quite a while, and many, or probably most, traditional data warehouses are sort of developed from an data architectural point of view of that perspective. The technology layers have also been pretty well established in traditional warehouses. You have the source systems spread out inside and outside an enterprise, a data integration layer, and traditionally that's been an extract, transform, and load, or extract, load, and transform ETL layer, where people grab things generally in a batch or near real-time fashion, pull the data, do cleansing to it, and then bring it into a warehouse. Traditionally, that warehouse, that layer, the data warehouse and BI data layer, has been relational databases. More and more, as we'll see shortly, the data marts of the BI schemas have drifted to other database schemas and structures to support much more varied analytics. And then on the business intelligence layer itself, we have reporting, dashboards, ad hoc query tools, data discovery tools, integration with spreadsheets and Microsoft Office, et cetera. So these layers have been there for quite a while, and that's pretty well how most people are operating today. Now the challenges, the next few slides are sort of talking about the challenges that people are facing, some of them quite different from what they did even 5 years ago. First off, the traditional warehouse brought data in from sources that the company, the enterprise, controlled. Now, they could be on-premise, they could be in the cloud, but the idea is that the sources were known and could be described and managed by the enterprise itself. Certainly that's changed drastically in the last several years. We're getting data from social media, from the Internet of Things, interchange of data between partners, suppliers, with customers, with prospects, et cetera. So the amount of data from where it's coming from, we move from a managed environment to one where they just can't control and might not even know what the contents are going to be. We also have various sources of data. Now, I know we keep hearing all about big data, and that's certainly a factor in this environment. But data isn't just coming from social media or from the Internet of Things. It's the interchange of data between who your customers are, your prospects, your suppliers, your employees, et cetera. All that is been moved up at a significant level of interchange in the last several years. And then the use of the data, the type of analytics. We go from firms that are $10 million to $100 billion. And you can have analytics and reporting that you never saw before 10 years ago, 5 years ago, even a couple years ago. So the need for analytics, the ability to run your business with that analytics to improve the efficiency of it, all that's happening with the explosion of data and the use of data. Now, one of the things that's happened, and one of the areas that has led to a lot more difficulty, has been we had a nice core bedrock of relational databases, but for a variety of reasons, our analytics and our data has grown beyond just what relational databases can do. We have many different types of data structures now. For a while, we had columnar databases and OLAP cubes. We still have them now. More and more, we're getting in-memory databases, in-memory columnar databases. data virtualization, many different other structures, big data structures that are being used just because we haven't been able to tap the ability to analyze the data as effectively or as quickly as we want to do. I don't necessarily mean real time, but the ability to get the data and start analyzing it. There's usually a large lag based on the complexity of the resources. Usually I don't put vendor logos on any slides, but I just throw in the core relational database vendors. Everybody knows this has been there for a long, long time. But the real play, what's the exciting part that's happening in the database side with changes in data structure, schemas, and technologies is outside generally these vendors themselves with a lot of different exciting technologies. And it certainly isn't just big data. There's many other data structures that are being used in databases that are having actually a far bigger impact on analytics today than even big data is having today. Not to belittle big data at all. On the data integration side, I'm certainly not going to talk about the details of this slide, but what I do want to say is that unfortunately people have narrowly focused their integration capabilities to ETL, whereas there are a wide variety, ETL, enterprise service buses, SOA, service-oriented architecture, JSON, data virtualization. There's a lot of different types of what I refer to as data integration channels that are available for integration of data from various data sources, which was absolutely needed with the variety of data we have. And just on the right-hand side of the data integration suites, the other thing that people aren't taking advantage of is the sophistication, the transforms, and the capabilities of the integration tools out there. People are still often, and one of the reasons why it takes so long to get things done, is still just writing SQL scripts in order to get things done and not leveraging the tools that are out there. With all these changes, we get to the sort of issues that we run with traditional data warehouses. One, there's too many tools. As you saw by the slides before this, there's a lot of moving parts. Two, and I guess this is sort of my high school picture. Actually, it's not, but people always think it is. You need a lot of really dedicated technical folks, nerds, to be able to put these things together in any coherent fashion. Third, it takes a lot of money and a lot of time to get these projects done. And the result is we have the business having an awful long queue in order to get their information and do analytics. We have a way too many variety of data silos and analytical silos that companies have, regardless of the investment they've making. And lastly, we just seem to be stuck in the mud as far as getting things done in this environment. I'll quickly go through some of the changes that are happening, and then we'll pass it on. First off, we're moving from a classic data warehouse-oriented architecture to more of an analytical data architecture. So rather than the stacked data sources, the data integration, the data warehouse, the BI, really want to think of data integration as a T, whereas data warehousing, BI data, cleansed data, data sources, it doesn't really matter. A business person, a person trying to analyze data, shouldn't have to know or care where the data is coming from, and they're going to have to intermix that data if they're really going to leverage it effectively. And this diagram just fills in the blanks of all the different technologies that are out there that are being used in order to fill this dream. Now, of course, this goes back to the fact that there's an awful lot of tools and a lot of people that are needed in order to be able to drive this home. Finally, one of the biggest areas, I think, on sort of this analytical data architecture is really the database layer in the middle. So we have all these different proliferation of data sources. We have much more robust and capabilities with business intelligence analytical tools, with data discovery tools, visualization, mobile capabilities, predictive analytics on the right-hand side. So we have a lot of that, but what we still have in the middle, and what you saw through various other slides, is there's two things we're trying to do. We're trying to integrate data from various sources. That's sort of the purpose of the enterprise data warehouse. And we're trying to set up information, these sort of systems of analytics, information set up so it can be analyzed. And unfortunately now, too many companies have to do a hodgepodge of different technologies in order to be able to solve that problem. So what I've seen a lot of advances lately has been in moving toward getting a more robust database layer section in order to be able to do it with less moving parts and be able to move to get solutions done much quicker. And with that, I'll hand it off to Robin.
All right, and Robin, let me give you the keys to the WebEx here, and take it away. Robin, do we lose you?
Sorry, I was on mute.
It happens. Go ahead.
There you go. Well, thanks for that, Rick. That was a really good, if you like, detailed positioning of the whole of the data warehouse space. And because I get to see the presentation of the other analysts before I ever even create my presentation, I just thought I would do a series of summaries around the space of data warehouse. With the question is, where are we going, Quo Vadis? Where are you going? The thing is that the data warehouse space itself is being disrupted at the technology level, and it's been undergoing disruption that's been getting bigger and bigger and bigger for about the past 10 years. So, you know, when we had, for instance, the coming into existence of what I would call the column store market and a whole series of column store databases fed in, and that was the first major disruption, and everything that's happened since then is just more and more disruption. Nobody is questioning the need for a data warehouse. I want to actually reinforce the whole thing. Everything that's happened, certainly in the past 5 years, with the trend to big data, and everybody talking about the wonderful gold that you might find in those mountains of data. Really, data warehouse hasn't changed for a long, long time in terms of its position within the organization. It is the feedback system. You know, it's not the real-time feedback system because data warehouses can't go that fast. But aside from that, it is the feedback system. And if you divide all of the computer systems that run into in an organization, there are really 3 types. So the communications and individual uses systems. They're called office systems. There's the OLTP systems that in one way or another are keeping track of where the organization is and what it's doing, and then there's the feedback systems. And if you're going to have a feedback system, then you probably need some form of data warehouse, and I don't think that that's going to change for a long, long time. And it was a BI engine in the sense that not all organizations used to do a great deal of analytics, but it's now become a BI and an analytics engine. The pretender to the throne is Hadoop. I'm going to dismiss Hadoop in this role. There are ways that you can use Hadoop to do certain things in the data warehouse space. Hadoop is inexpensive with a question mark because the question mark means you have to hire people that can configure it and use it and know how to do that. And that could be more expensive than paying a data warehouse license. It can handle any data simply because it's a key value store and it isn't a database. It may have metadata and it may not have metadata. There are issues you can get into trouble with. It has poor performance, despite the fact that it's incredibly parallel in the sense that the whole thing is scale-up and parallelized. It actually doesn't perform particularly well when you compare it to any kind of data warehouse engine. It's got weak scheduling capability. It used to have none whatsoever. It's now got something called Yarn that allows a kind of scheduling capability and a kind of resource sharing, but it's not sophisticated yet. It's got very weak data management. Security, we're going to have to buy it from someone else. It doesn't come with the stuff. And really, it's a data lake. You don't use it as a warehouse for data. You use it as a place to put lots of data while you do lots of things. Rick described the source and ETL part of it precedes data getting to the warehouse. A lot of that is data lake activity in Hadoop. And if you stuck Hadoop in front of as a kind of staging area in front of a good performing data warehouse, it's probably going to serve you reasonably well in that environment. The data warehouse, the enterprise data warehouse, expensive, yes. Prepared data, yes, it has to be modeled. It will have metadata. In fact, you can't put stuff in there without metadata. Performance will be optimized. The schedule will be optimized. There'll be good data management. It will be secure, and it will be a data workhorse. You know, and those two things are distinctly different. And I don't see Hadoop coming anywhere near what a data warehouse can do anytime soon. But, you know, we have no idea what it'll look like in 5 years' time. So I've got two columns here in terms of dimensions of disruption. These are just really, if you like, comments that I'm making as to how the whole of the data warehouse technology itself. So I'm not really talking about Hadoop. I'm actually talking about things that call themselves data warehouse. First of all, there are cloud deployments nowadays, and there's a huge advantage in the cloud in various ways for certain kind of cloud businesses, and I believe that data warehouse can be a cloud business. We're getting on the hardware side, CPUs and GPUs are merging. Commodity servers and commodity storage is becoming more and more pervasive, and the price differentials are becoming greater and greater. We've got on-chip processing, we've got memory-based architectures, we've got virtual networks, we've got parallel software coming out of our ears, we've got parallel environments. If you just take all of that together, what we're actually talking about is we're talking about huge hardware disruption that makes it possible for a data warehouse to perform far better than it ever did before. However, you actually have to have the software that can do that. So there's a question with any data warehouse technology is how well does it exploit the hardware that actually exists, because that's what it's for. It's supposed to be something that makes an engine run on that hardware. Down the right-hand side, we've got the other disruptive factors. I mean, first of all, data volume. So the old data warehouses of the past, which were really quite good, most of them didn't really scale out. You know, so they would run on fairly healthy clusters, but when you got beyond, you know, a cluster of 8 or even 16 machines, you're suddenly into an environment they were never built for, you know. So the data volumes cause serious problems. You've got the Hadoop and schema on read situation that's causing a problem because some data will travel with its definition, and therefore is kind of pre-modeled, and you could, in some ways, you need to be able to accommodate that data within the data warehouse more swiftly than you ever did before. We've got the unstructured data situation. An awful lot of the data that we're gathering nowadays is unstructured, is worthy of analyzing as well. We've got event data from the Internet of Things, which is a different kind of data, so we've got more variety of data than we ever had before, plus more volume. Data availability in the market for data is starting to rise up. In other words, the actual value of the data itself is becoming an issue. And then we've got, and Rick pointed this out as well, we've got analytic workloads and we've got analytics tools, and that's changed the nature of the workload that sits over the data warehouse. You know, and if you put all of that together, you know, what you're talking about is an opportunity for new database technologies to step forward, because a lot of the older technologies are constrained basically by design decisions that were taken quite a while ago. And new technology doesn't necessarily need to be constrained like that. And that's what we're talking about today. Snowflake is such a technology, and I'm hoping that we'll get a lively discussion about its capabilities and its limitations. So the questions I have that, you know, that I'm going to pose to Bob, the general questions to set him off, because he's about to present the nature of his technology. What are the characteristics of an appropriate data warehouse? What should one be nowadays? You know, and the second question: should it live in the cloud? Is that its appropriate location? And with that, shall I hand it to you, Eric, or hand it on to Bob?
Yep, I just handed the keys over to Bob. Just click anywhere on that slide as you stand here.
Great. Hey, thanks a lot, Rob and Eric. Really appreciate that. You guys have done, both Robin and Rick did a great job of setting up this discussion, and I look forward to talking a bit about how Snowflake is truly revolutionary and really can change the entire nature of working with data, and that's both structured and semi-structured transactional and machine-generated data. And so let's talk about that. So in the so Rick, one of your sort of slides, you sort of talked about sort of the structures of data warehouses, and this slide is really well, a lot simpler than your slide. It basically sets up the same sort of thing. Classically, if we sort of go back in time, and I'm a sort of historian at some nature, and I've been in the database game for a long time. I always have believed that data is the fundamental intrinsic of the way applications are built, and data structures are very fundamental to how applications behave. And I go all the way back to the codicil databases and the ISAM databases of the late 1970s and 1980s, and when I found relational and really got into SQL in the 1980s, and particularly when I started at Microsoft working on SQL Server in 1988, it really has revolutionized the way people work with data. And then we've seen over time how analytics have grown out of that, and we've seen the importance of analyzing data and the separation of data analysis systems, data warehouses, from traditional OLAP transactional-based systems. But what we've seen as the data warehouses, the modern on-premise data warehouses sort of emerge, we've seen certain characteristics come into place associated with that. Amongst them, the fact that these are complicated machines, they tend to be packaged in the form of an appliance, purchased in that sort of way. Very often data goes through a complicated transformation process before it gets into the system. And then, as you discuss, as Rick particularly discussed, there are a series of systems that tend to surround the EDW to provide the ability to do analysis. The data mart being one of the most important of which, because it allows for a separation of, it allows multiple teams to work on data independently. That's the fundamental thing. And traditional EDWs struggle with that because they have limited capacity and they tend to be quite expensive. So these data marts and other OLAP systems and things like that tend to sprout up like mushrooms around these things to allow multiple teams to work independently. But if there's been one tenet that has been present for a whole long period of time that I think has been a principle that's been applied to the way you work with and manage data, it's that you gotta co-locate storage and compute together. This has often been referred to as bring the compute to the data because the data is hard to move. And that's been sort of a fundamental way in which all data systems have sort of been built, certainly the traditional data warehouses, but also the new so-called big data systems like Hadoop, which also have that idea of co-locating data and compute together. Now, some challenges have sort of emerged. Some interesting things have happened. Disruptions have emerged that challenge some of these fundamental conventions that have existed for so long. The two that I've chosen to highlight here are really the advent of cloud infrastructure and machine data. Let me take machine data first. If you go back historically over time, data warehouses were built to handle transactional systems. And these date back, certainly into the 70s and 1980s, but they became popular in the 1980s with the advent of relational SQL-based systems. And certainly companies like IBM and Oracle and others, ultimately Microsoft, built systems that were used as the foundation for which transactional business systems were built. The data is structured; it's in the form of columns and tables, of course. As we sort of have emerged, in the more modern era, the advent of machine-generated data has become very important, coming out of internet applications, cloud apps, data devices of all kinds, both mobile and otherwise, as well as sensors, things like that. And we're actually have reached the inflection point where more data is generated from machines, typically in a semi-structured format, often in a file in JSON or Avro file format. But in general, more data is actually generated from that in that way today than is generated from the traditional transactional systems, largely because machines are really good at doing things quickly. And now, the other change that's happened that sort of turned some of this on its head is the advent of the cloud and the importance that the cloud has to organizations in a way of actually doing their IT in a different way that is potentially much more efficient than what they could ever do before. One of the things I will point out is about the cloud, and this is where I kind of refer back to the previous slide and some of the things I said, is that the cloud is, you know, an all-new set of technologies that are really very fundamentally different than what preceded it in the on-premise systems in the world of virtualized infrastructure. You know, the fundamental of infrastructure as a service in the cloud is the idea that you've got the ability to instantiate things in an immediate way, and the system automatically allocates the resources. It's really about the system allocating the resources. So you have the ability to bring resources up and down on demand in a highly elastic way. But the other thing that's really interesting is some new technologies like the advent of blob storage, very durable, very cost-effective, extremely cost-effective storage that can be used for long-term storage of data that has some interesting characteristics. I mean, blob storage, let's take Amazon and S3, it's incredibly effective, but it does not have the access and latency guarantees that you would get from a traditional SAN infrastructure. And so, you know, normal systems can't tolerate direct access to that storage, but it's incredibly useful, and it's a brand new technology that existed. You know, I mentioned the instantiation of virtual machines on demand, and hardware on demand clusters can be brought up in just a couple of minutes instead of days or weeks or months. And the other thing that's really important that just turns on its head that old view that you got to bring the compute to the data is the advent of 10 gigabit Ethernet has allowed for highly performant, very, very cost-effective connections that allow you to separate the data from the compute. Now, if you go back to all of those systems that I talked about a couple of minutes ago, all of those systems, whether they're Teradata or Netezza or SQL Server, good old SQL Server, or anything else, Oracle, all these things were designed in an era where none of these things were available, that you didn't have the cloud, you didn't have blob storage, you didn't have 10 gigabit Ethernet, and you sure as heck didn't have virtual compute on demand. Hadoop, also 10 years old, 2005 it came out. All of that was built in a different era with an architecture that made sense at that time, but, and you know, it's fine. It's a good, solid, working architecture, traditional, some might call it legacy, but it works. And what it doesn't do, however, is take advantage of in any fundamental way what the cloud can deliver. So these disruptions, the advent of a broad amount of machine data, and of course, we all know that traditional data warehouses can't handle machine-generated data. They can't handle semi-structured. You know, Hadoop can, although in a highly inefficient, poorly performing way, but it can handle it. It's the only option that most customers have available. All of these things, you know, are turned on their head because of the disruptions in the cloud and the machine-generated data. So enter Snowflake. Snowflake was built in the post-cloud era. We're the only modern data warehouse. We're the only data warehouse on the planet that was designed, built from the cloud up. All of the technology in Snowflake was written by Snowflake. It does not utilize any of the pre-existing open source software like Postgres or MySQL or Hadoop to do what we do. We built this to be the modern data warehouse for the cloud era. And we took advantage of the capabilities that we had available to us because we built it from scratch. Things like blob storage that provides, you know, essentially limited storage, on-demand compute, fast networks, to separate the storage from the compute and deliver a very different experience. The architecture we're built on is really a completely different architecture than anyone has ever used before. We're neither shared nothing, nor are we shared disk. We are really shared data multi-cluster in our structure. So the idea that you have one centralized data repository that can be used by multiple clusters at the same time. And you see that in this architectural diagram. The database storage is just cloud blob storage. Now, we run on Amazon, so that means S3. And we just leverage the fundamental capabilities of S3 to store essentially a limitless amount of data. And then on top of that is a set of virtual clusters. We call them virtual warehouses. They're instantiated on behalf of one of our customers, and they are essentially a compute cluster that is used to access and work against that data. And the distribution of that data, that cluster, is fully dynamic. It's done on demand at the time the query is run. Not beforehand. The data is not preloaded. It is all brought in as the queries are run. And because of the way we've structured this, we can get incredibly good performance on that. The secret sauce, so to speak, that makes it work is we have a layer on top of that that we call here in this diagram the cloud services layer. And that has associated with it a central brain. It's the center of the service. It's the service endpoint, but it's also the point where we perform query optimization. We have a centralized distributed metadata store in there that knows everything about the data. It doesn't have, it has a fraction of the amount of data. It doesn't have any of the customer data in it, but it knows the information about the data, including statistical information to allow us to perform effective query optimization and pruning. And because we have this centralized brain that can tell the virtual warehouse what to do, we get incredible performance out of this system, the ability to run massive amounts of data, hundreds and hundreds of terabytes of data against these large instantiated clusters that can very, very effectively pick out just the data that's needed to perform these queries super, super fast. So this architecture that Snowflake has built has been created from the cloud up, totally unique, totally new, and it enables really a revolution. So what is possible with the Snowflake architecture with what I've described? Well, it is truly, I had this incredible opportunity in the last set of months to talk to customers that have been working with data warehouses in some cases for decades, and they have in their mind the way things work. And their head is kind of in a box. They know what the box looks like. And we come to them and we talk about what Snowflake does, and they sort of stare at us blankly, and they think, you get these conversations and they're like, wait a minute, are you really, what are you saying here? And we kind of go through and explain to them what we do, and then we explain how we do it, and they go, maybe that's possible. And we go, yeah, it actually is, try it. And then they try it, and they come back and they go, oh my God, I've never seen anything like this. I mean, queries that took an hour and a half take 2 minutes on Snowflake. How can that be possible? We have all this JSON data we're loading into a Hadoop cluster, and we munge on that cluster for hours at a time, and then we feed it out and spew it into a data warehouse, and we have analysts working off of that. With Snowflake, we just load all that JSON data right in, and analysts can use the tools they know, Tableau, Excel, MicroStrategy, Looker, whatever it is. They can use those tools directly against this JSON data, and they get answers in 100th, literally 2 orders of magnitude faster than they were getting on Hadoop. How is this possible? And the answer is really the architecture. It's all about the fact that unlike all of these pre-existing systems, all these Hadoop systems, all these traditional data warehouses, Snowflake was designed for the modern cloud, using modern cloud technology, and the results are pretty spectacular. So, the fundamental characteristics of what's possible, well, first of all, it's a service. Snowflake is a full SaaS service. Think Salesforce. We're just like Salesforce. You load the data, you run the queries, we do everything else. The system was built to have no knobs, no tuning required. You just run your queries and it works. If anything goes wrong, we fix it. I mean, we're updating it all the time. We're monitoring it. We encrypt all the data. We're the only system that encrypts all the data. We think that's super critical in the cloud. Turns out that security is a top priority for everybody. It's certainly our top priority. So we don't see the customer data, but we see how our system runs. And when something goes wrong, we fix it. In fact, most of the time, we're able to fix the problem without the customer even seeing it. If a query fails, most of the time we're able to, because we lose a node, for example, we're able to just repair the cluster, rerun the query without the customer even seeing the failure, and then continue on. So we're a service. We maintain the thing. It has no knobs and tuning. It's really incredibly simple compared to these traditional systems. The second thing is because we're built on the cloud, we provide, what we call sometimes multidimensional elasticity, or what I tend to think of now as infinite elasticity. Infinite amounts of data, infinite amounts of compute, infinite amounts of users. So the ability to have as much data as you possibly want, to make your queries run as fast as you want, or to put, have your workloads complete as quickly as you'd like them to complete, and to put as many users on. Because we have multiple of these virtual warehouses operating simultaneously against a single shared data set, there's no limit on the number of users you can put on. The physics of any cluster, any set of physical nodes says there are limits to what that cluster can do. and there's only so many things you can do at the same time. And in every other system, every single other system on the planet, when you hit that limit, you need to build a new cluster with a new copy of the data and maintain those copies in sync, and it is a royal pain in the derriere. Unlike that with Snowflake, the data is all separated from that. It is all shared. It's all transactionally consistent. You have multiple clusters running simultaneously. If you have more users than if your SLA requires more users than a single cluster can have, you can instantiate a second cluster or a third cluster or a fourth cluster, operating on the same data at the same time, working simultaneously. You know, 1 user, 10 users, 100 users, 1,000 users, it all works, you know, and scales essentially infinitely. And then, you know, I mentioned the fact that we work with both structured transactional data and semi-structured machine-generated data. That is the reality of the world for many of our customers. And, you know, for many other customers we talk to, they're staring at this machine-generated data, wondering what the heck are they going to do with that data, because they don't have the expertise to be able to do. They look at this thing, they go, my God, it's so complicated. I need to hire all these people. I need to figure this stuff out. You know, here I am sitting in the middle of Silicon Valley. There are a few companies around me that can do it because it's the center of the tech, you know, where the tech guys all are. But you go out to most customers in most parts of the world, and they simply don't have the expertise to do it. With Snowflake, it's super easy. You read the data in, you run a SQL query, it just works. Technically, what we do, for the background on this, why can we make this so good? Technically, you know, we're a columnar store. When you read semi-structured data in, you know, semi-structured data is diverse. It has different shapes associated with it. When you read semi-structured data into Snowflake, we ascertain and discover repetitive attributes in that data. We columnarize those attributes. We collect statistics from it, which we store up in our services layer. And then when a user runs a query, just a standard SQL query, they run against that semi-structured data. We are able to do the same level of optimization, the same level of pruning against it. So we run it at very close to the same speed with machine-generated semi-structured data as we do working with structured data, which nothing else does. And we provide the ability to put standard tools, you know, Tableau or Looker or Excel sitting right on top of that. And have, you know, one step to solution in an area where before it was a complex nightmare. And then, you know, sort of to top it off, we just happen to provide the best price performance in the industry. We provide zero upfront costs, so you don't have to buy this expensive system and take months to install it and all that kind of stuff. Zero upfront costs. And if you look at your ongoing operating cost, it will be a fraction of what any other system is, including comparing to other cloud-based solutions, because our architecture provides us with fundamentally the ability to use hardware much more effectively than other systems do. That's a summary of Snowflake. It was a whirlwind tour. I kind of went quickly, I know. But hopefully I covered a lot of ground and can open it up for questions. And let's take the next step with you guys.
Yeah.
Pass it back.
I've got a couple of questions I'll throw at you real quick, and then I'll turn you over to the wolves, by which I mean analysts, but they're nice wolves. No, but seriously, you've done some really interesting things here in terms of the architecture and in terms of being able to very dynamically spin up resources. You talked earlier in the show about how one of the nice things about the cloud is that you can instantiate some piece of software, like a virtual data warehouse, for example, and it'll provision the resources very, very quickly, and you're up and running. Can you talk about why that happens? And then I have one more question before I turn you over to the analyst.
Well, I mean, what we did is, you know, first of all, we leveraged the underlying cloud infrastructure, as I mentioned, that we run on Amazon today, and we very much leverage the fact that a fundamental of infrastructure as a service is on-demand compute resources. You know, so we're able to provision. You know, we have to centralize. Our centralized data store is S3. It is the only place where data is actually stored permanently in Snowflake, is in blob storage. When a virtual warehouse is instantiated, you know, it is done on behalf of a customer. It is of different sizes. We use simple sizing, you know, small, medium, large to describe it, but underneath it's a certain number of EC2 nodes that get instantiated, and what we do is we access the data as we need it. So unlike most data warehouses, and really any other MPP-based system, we don't have to require the definition of a distribution key of any form to pre-distribute the data in any way, shape, or form. And we certainly don't pre-populate the nodes with the data before queries can be run. We have an internal set of algorithms, hashing algorithms, to allow us to know, based on the queries that the users are running, exactly what data we need to fetch from S3. Now, the local nodes in the cluster have some flash storage on it, and we use that to temporarily cache the data. So if another query is run, when another query is run, I should say, the data that is when it's utilizing the same data as the previous query, we can pull that right out of flash and thus improve performance somewhat. And very quickly, as you would imagine, the hot data winds up getting cached on this cluster. But there's a very small penalty to that, really. The first couple of queries are a little slower than the rest. But our recommendation to customers is that they start, that loading might be done 24/7. We recommend customers have a loading warehouse, a small loading warehouse running all the time, so that the data is always in near real time in their system. But for analysts working on the data, we recommend that a virtual warehouse is started at the time the analysts are working, say at 8 in the morning, and when they go home at night, 6, 7 o'clock at night, the warehouse can just be paused, and at that point, it basically goes away, and you're not paying for it until you actually use it.
Okay, good. And so you also talked about, and you just referenced this now, I believe, a moment ago. You talked about how the system is very good at identifying which pieces of data or which data sets are necessary to fulfill a particular query. Now, is that driven by a sort of metadata cache or something?
It is.
How exactly does that happen?
It is. I mentioned that there's this services layer, and that's the brain of the system. Up there, we have a distributed metadata store, a highly available metadata store. One of the other attributes about this, there's some incredible things that can happen when you build on the cloud. I mentioned that we encrypt all the data on disk all the time. We're obviously encrypting in flight over the internet as well. But one of the things that's really interesting is we built the system to leverage the availability that the cloud can provide. So we actually run this distributed system across multiple Amazon availability zones simultaneously. So we can continue to keep the system operational and up and running, even if there's a loss of an availability zone or a data center, and certainly the loss of servers and things like that. So the system has built-in availability like no other system has, and it's just part of what you get when you use Snowflake is that fundamental availability. But that metadata store, which is distributed, and highly available, contains the essence and the brains. It contains the information that allows our services layer and our query processor to determine exactly what data needs to be fetched. So, as the data is loading, we're collecting statistics and metadata about that data, and we use that during the query, the QP process, the query processor process, to determine exactly what data needs to be scanned by the virtual warehouse. So if you've got 100 petabytes of data, we literally have a customer that has a single table that's approaching 100 petabytes in size, 100 terabytes, I'm sorry. If you have 100 terabytes of data, which, by the way, this customer with this table that's almost 100 terabytes, uncompressed, that's compressed, uncompressed, it would be approaching a petabyte in size. If you've got 100 terabytes, no matter how many nodes you've got, it's going to take a while to scan that whole table. But because we have information about that data, when they run, almost every query they could possibly run, we only have to pull a small subset of that data in and actually do the scan on that. So we're able to achieve, orders of magnitude better performance than similar systems, particularly when compared to Hadoop.
Yeah, I think this is wonderful stuff, and I could chew up all your time, but I figure I should let these guys jump in here. Maybe Rick, if you have any questions, and then Robin.
Okay, great. Yeah, it sounds very exciting, Bob. So particularly I wanted to maybe just stay a little tiny bit on the metadata layer. Now, certainly with semi-structured data, I can sort of see how you can, when it gets ingested, understand the context of the data. But how do you do that? Is there happen to be any definitions of the structure of the data in relation?
Yeah, that's a great question. That's a really great question because one of the core issues you have about semi-structured data is discerning the schema of it. We operate in a schemaless fashion on query. So what we do is we essentially dynamically create the schema as the data is ingested. And one of the attributes of semi-structured data is that it is not it is dynamic in its shape. Over time, the shape of semi-structured data tends to change. This is because, most of the semi-structured data, of course, is coming out of machines that are reporting on information that was added by programmers who tend to add attributes to that data pretty much willy-nilly as they think are interesting, and they certainly don't tell the data analysts downstream when they're adding attributes. So it's incredibly painful to try and predefine a schema associated with semi-structured data. What Snowflake does is, as we read the data in, as we ingest the data, we compress all of it, and when we find attributes that are, what you see is at different levels of the hierarchy in semi-structured data, you see attributes that tend to repeat itself. And, they may repeat itself today, but then tomorrow it may not be there and something else might be there. So what we do is, just as we're reading it, in blocks, we look for attributes that are repetitive, and we go, aha, that's interesting, and we columnarize that to efficiently scan it in the future, and then we collect statistics that we store in the metadata layer about that. And, we keep all of these attributes, the accumulation of the attributes that we find that are interesting, we keep that information and sort of essentially dynamically form a schema that allow you to do queries against that data and use it in the predicate clauses of the SQL on that.
All
so
right.
it's very unique. Nobody else does this. And by the way, we're patenting all of this. Nobody else does what I just described. If you look anywhere you want to find it, no one does that.
Oh, that sounds terrific. Certainly the columnar and the indexing concept makes a lot of sense to me. I still go back to, you can be real quick or we can just not dwell on it, but on the structured data, how does an analyst prescribe what that structure is beforehand? Or?
Yeah, we look fairly traditional in terms of structured data. We're a columnar store. We do sophisticated data pruning and query processing on it. We're very, very performant relative to other traditional data warehouses. But typically what people do is they build, they will typically use a star schema of some form to put their structured data in. Now, because of the way we're designed, and, I could get into depth about this, but because of our design, we do a lot of our query processing optimization dynamically at runtime. We tend to be more tolerant of different structures than many other databases are. If you look at many of the other databases in the analysis, in the data warehousing space, if you didn't structure your schema in a particular way, you get really poor performance. And in general, we will do better than many of those databases will, maybe even most of those databases will, if you have not if you've not created an effective schema. We can still process it very effectively. We certainly support very, very complicated joins. I've seen query, one of the things about Snowflake you may go, oh, this is interesting, but, what kind of SQL do they support? Well, the reality is we support the full set, the whole shebang of ANSI SQL. We run TPCH very performantly. We run TPCDS, and if people are familiar with TPCS, we run all the queries of TPCDS. You can find production quality data warehouses that have been on the market for 10 years that don't run all the queries of TPCDS. If you compare it to Hadoop, of course, that's just a tiny fraction of either of those. But, our SQL is very complete. And we've had customers that have thrown SQL at us. You go, oh, my God, look at the SQL, how complicated it is. And we run it. We run the whole thing and do so very performantly when compared to traditional systems. What we hear again and again is, customers have Oracle, customers have Netezza, customers have Teradata. They come to Snowflake and they're getting, significantly better performance than they're seeing on these legacy systems, once again at a fraction of the price.
Oh, that sounds terrific. Do you have questions, Robin?
Yeah, sure. I've already been briefed on the technology, so to a certain level, I'm not particularly, I don't want to try and dig into the technical side of stuff because I kind of sort of know it, and I think you explained it reasonably well, Bob, anyway, to the extent that you can in the time available. I'm interested in, first of all, you seem to be outperforming Hadoop by orders of magnitude, and that doesn't surprise me. I would like a little bit of context in terms of comparing you with, let's say, a big Oracle, because you just mentioned that you'd be less expensive, but also you will outperform some of the legacy products. And if you could put, without, just put a rule of thumb or some kind of feeling as to what that distinction actually would likely be for somebody out there.
Well, it's hard to say there's a single number because there's times when we perform, unbelievably better than those systems, and there's times where possibly those systems in certain situations may perform better than us, or we perform roughly comparable. On average, I would say we do a lot better than those systems. Maybe, for most things, 3 to 5 times faster. For a lot of things, certainly at anything close to the same price point, we way outperform. We way outperform them. The benchmarks we've done. We've done a number of benchmarks head-to-head, and we tend to find that because of the design of the architecture, we are often on the order of twice as fast per core as other systems are, if you just use that as a comparison. There are going to be edge cases, though. I'm not going to tell you that every single query we're going to do that on. I'm going to be straight and say there's times when we might not perform as well. One of the fundamental differences between Snowflake and, let's say, Oracle, our founders came from Oracle. They know Oracle inside and out. And one of the fundamental differences between an Oracle or any of the traditional databases and Snowflake is those databases are designed to be tuned and optimized by a DBA. And Oracle was always legendary for having 1,000 knobs that you need to tweak. And certainly it is possible that if you have a DBA sitting there tweaking those knobs day in and day out, focusing on this particular query, there's a very good chance they'll get that query running faster than you might get running on Snowflake. But then if you do anything different than that, it may not perform so well. And what we've done, which is very different, is build a system that has relatively uniform performance across a wide range of queries. And because the system is designed without those knobs, and it's just designed to work very quickly and in a very consistent way across a wide variety of queries and a wide variety of workloads, the overall performance, it turns out to look stunningly faster than what these systems tend to do. So, your mileage may vary. I'm not going to say this is the reality of the world is that there are many different things. And we're always interested when customers bring us queries where there's opportunities for us to improve performance. And I'll tell you one of the great things about it. We're a SaaS product. We're updating the product constantly and improving it day in, day out. All of our customers are running the current version. So think about Oracle. God knows what versions you're running, how old those things are. All of our customers are running the version that we installed literally yesterday. And so when customers bring us things where they say, geez, we think this could perform faster, very commonly, about 3 days later, we're beating the competition because we got the team that is able that knows everything inside and out. We're able to, look at all the intrinsics of what the customer, what that query is doing, have access to all of the metadata about it, and go, aha, this is an area where we could improve our, our optimization or whatever. So our results are, are much better on average.
Okay, and just to kind of clarify, what's the pricing structure like? How does that How does that work? Is it by data volume? What is it by?
It's exactly. It's essentially capacity based in its nature, and so you pay for two things in Snowflake. You pay for the amount of data you store. We measure that data in terabytes because that's the sort of sizes our customers are typically working on, and then it's also based on the number of on how large these virtual warehouses are that you're running and how long you're running them. And so we have a simple table that based on the size of the virtual warehouse, you consume a certain amount of what we call a Snowflake credit. And we've normalized all of this to something called a Snowflake credit, and you consume a certain amount of that per hour for every virtual warehouse you're running. And on average, it's 100 credits per month per terabyte. Our on-demand price of that, which means if you just come up to us and do a deal where there's no commitment on your part, it's $2 a credit. But then we discount that for customers who are buying capacity up front.
Okay, good. And we got a couple of good questions from the audience. I know we're already at the hour here, but we got a bunch of people still tuning in. So I'll throw just a couple of these over to you, Bob, and thanks again for doing the show today. So one of the attendees is writing, so if everything is in blob, then the intelligence in the services and metadata layer and runtime generated schema is the secret sauce in the software. Is that right?
Yeah, basically, I think what you described is really quite right. It's runtime we distribute the data dynamically, and we're very smart about what data we need to access. So we only, we only access blocks of data at a time. In fact, we actually got it down to the point where we only access the column. If you've got a table that has 100 columns in it, and some tables are much bigger than that even, we don't need to access the whole table off of blob storage. We can actually access, only accessing, say, 2 or 3 columns. We can pull just the 2 or 3 columns. It's all about really, performance is really all about how much data you have to scan and effective utilization of the CPUs. That's really the whole key. People think that data warehousing is I/O bound. That turns out to be not correct. Our system is CPU bound, and the goal is always to be CPU bound. You want those CPUs running at as close to 100% utilization as you possibly can. And so the goal is to keep the CPUs busy while scanning and fetching as little data as you have to make that work. And so we're just super clever about how we do that. And if you ask the question, well, how the heck do you do that from S3, which, is not known to have a low latency associated with it? In fact, one of the things I describe about S3 is the key characteristic about it. It's a remarkable system, just remarkable in its ability to store massive amounts of data with very, very high degrees of durability and amazing degrees of concurrent access against it. But the one attribute about S3 that is rather problematic for a database is the access time of S3 is roughly indeterminate. Sometimes it's just a few milliseconds, and sometimes it's a second. And of course, a second is roughly an eternity in this world. So, how do you deal with that? Well, the answer is, there's 2 answers. One, you prefetch the heck out of it. So, the virtual warehouse knows how to prefetch the data out, so the data is already on the node before the CPU is ready to work on it, and that's very important. But the other thing is you're very tolerant of, because we built this code from scratch and we're able to build it that way, we're tolerant of areas where there's little hiccups in S3, which there are all the time.
Yeah, and I love this schema on demand concept, and it's not the only place I've heard about it. There's one other place in particular, this program or the project called Apache Drill.
Yep, I'm familiar with it.
Yeah, can you talk about what you're doing and how it works? Because to me, it's a very, very clever way of attempting to streamline a particular process. And I'm guessing that what happens is you also have the audit trail and the ability to trump what it may determine, or to, in other words, determine before something happens dynamically that it should go this way or that way. Is that right?
Yeah, I mean, Drill is doing some clever things, particularly around it is schemaless in its architecture. The only thing about Drill is that it has to sit on something, and if it sits and it can sit on any, it can sit on a wide variety of data sources. If it sits on top of Parquet, well, that really does require pre-declared schema. So it's if I understand all that correctly, they're doing some clever things, but there's areas where I think what we built solves the customer problem more directly. And I mean, what we do, as I sort of said, is we determine the schema as the data is loaded. We populate our metadata store with that information so that you can use standard SQL to perform queries against that. Now, obviously, standard SQL, the standards don't have a consistent way of expressing access into a hierarchical semi-structured store, so we've made some extensions to SQL, like there's a dot notation that we use to address the attributes that are nested down within the hierarchy. But with that, we can then perform any relational operation. I want to be very clear. We're 100% SQL. We're 100% relational. We are a relational engine through and through. Remember I mentioned about the importance of the data model at the beginning. Putting SQL on MapReduce is a path to disaster because you have a semantic mismatch between the underlying engine and the language on top of it. SQL is the language that ultimately IBM did, that came out of the work that Codd and Date did in the 1970s when they created the relational model. And so we build and allow the full set of relational operators against both structured and semi-structured data. So you can do joins and group bys, and anything you possibly could do with structured data, you can also do with semi-structured data.
Yeah, well, this is fantastic stuff, folks. We went a bit long here. We do have some questions we didn't get to. I'm going to be sure to pass these along to our folks here who are presenting today so they can respond to you offline. But I just think this is really, really interesting stuff. You seem to be doing what Spark does, but in a much more enterprise-focused way, I suppose, where it's much more, does that make sense?
I think there's a lot of actually with Spark in particular, I think there's a lot of complementary aspects to what we're doing. Actually, there's definitely attributes of Spark that are interesting. So what I would say is, Spark trying to build SQL on top, the best, use of that would be to push all that down to Snowflake because we'll process it super effectively. But there's a lot of attributes about the use of Spark and the way they parallelize R and parallelize and enable machine learning things. Those are quite interesting. But yeah, I think when compared to Hadoop, and sort of the brute force mechanisms that Hadoop uses to try and solve some of these same problems, I think Snowflake is, orders of magnitude ahead.
Well, this has been great stuff. I know that I was impressed as soon as I heard what you guys had done. And it really speaks to the potential out there for anyone else who is planning or working on a project right now and trying to develop some software. It really speaks to the importance of understanding what you can now do with these different kinds of architectures and to the power that the cloud brings. Now, these guys obviously have been working on this for some time now. They just came out and rolled it out GA. So it always is going to take some time to build out a new database platform or application. But there is some really powerful stuff available to these folks out there today, guys, and I'm really happy to have them here in our show. And with that, we're going to bid you all farewell. Thank you so much for attending this Hot Technology Show. We ended the first half of 2015 with a bang here at the Bloor Group. Yours truly just did 5 webcasts in 3 days. So it's time for a break. Thanks again. We'll catch up to you next time, folks. Take care. Bye-bye.